Welcome back. In this video, we're continuing lesson 2. We're revisiting the problem that we solved in videos 12 and 13. This time, we're going to solve a linear equation using a graphical method. Let's take a look at the problem statement. We'll read the entire thing out loud to ourselves real slow so we know what we're supposed to do. Problem 4. Complete all 5 steps of graphical technique to solve the equation 3 times 2 minus x equals negative 8 plus 1/2 x. Sounds like we're going to do a graphical technique and this claiming that it's an equation. Let's ask ourselves that first question. Is there an equal sign in this statement? Boom. Yes, there is. In this case, we're going to solve the equation. Not only are we going to solve the equation, we're actually told what technique we're supposed to use. Before we jump in, let's do a quick recall of the steps of a graphical technique. We remember from our previous work that to find the solution or solutions, there may be more than one, to an algebraic equation using a graphical technique, we're going to complete 5 steps. Step 1 is to identify and graph the function on the left-hand side of the equal sign. We're told that we need to identify and graph the left-hand side of the equal sign. Look what we see here. The left-hand side of the equal sign is defined as 3 times 2 minus x. We'll go ahead and define y1 to be 3 times 2 minus x. We saw in a previous video that we had kind of 2 choices to fill out this table and then plot the points on the graph. Choice number 1 was to feel a lot of pain. In other words, do all these evaluations by hand. Choice number 2 was to use technology. Well, I'm all about the use of technology to make life a little easier. I think that's why I designed these darn things. Y1, we're going to define as 3 times parentheses 2 minus x. Close parentheses. Remember, the minus is the long one. The negative is over here. Now we want to fill out the table. We remember that the table button is actually the graph button, but we got to hit the second functionality. The reason that each button has many options is because the engineers that designed this recognizes that if you only had one button for one option, this thing would be absolutely huge. So doubling up or overloading buttons allows us to save space. Anyways, second, we see the little arrow in this case right there. That means I'm going to get to the table. We're lucky because this table starts at the negative 2 input value, and we can just fill out all of these entries. If our memory is turned on, we probably recognize all of these values from the work that we did in previous videos. Now we recognize that we can write each input-output relation as an ordered pair. I'm going to go ahead and fill all that out and fast forward the video so you don't have to wait for me to finish that. Now that we have each of the input-output pairs, let's go ahead and graph. Again, I'll fast forward so you don't have to suffer through all the details. In blue, we see our y1 function graphed. Let's return to our graphical technique. We have just finished step 1, which was to identify and graph the function on the left-hand side of the equal sign. Let's move on to step 2. Now we're going to identify the function on the right-hand side of the equal sign, and then we're going to graph this function on the same axis we used in step 1. Here we return to our equation. Here's the equal sign. We see this expression here is going to make up what we call the right-hand side of the equal sign. And in this case, we're going to go ahead and graph that using this definition. Once again, we have a choice to feel pain or to be strategic. Let's be strategic and use technology. Here we go. We bring in our TI calculator. We're going to define y2 to be negative 8 plus 1/2 x. I want to define a y equals, so I hit the y equals button. I've already defined y1 to be this y1. Now I want to define y2. In this case, I have a negative 8, so I hit the negative button, plus 1 divided by 2 times x. Some of you might want to make this 1/2 look a little bit more beautiful. All I did there was to delete. Do you see this little F1 up there? That means function 1. It's in green. If I hit this alpha button, alpha F1, do you see N over D? That means numerator over denominator. And this is a super fancy calculator. It allows me to actually write it in the same form as I read it. Now that I have the second function, the function on the right-hand side of the equal sign, defined, notice it's defined in Y2 and it's red, I'm going to go back to table. Table is written in blue, so I hit the blue button. I go back to table. Now check this out. Here my input is written x equal -2, -1, 0, 1, 2. My output for the Y2 is actually written in red and corresponds to these values. I can now use this calculator to fill out all the values associated with it. That's kind of giving me a headache right now, so I'm not going to trip about that for a second. So -9, -8, looks like every other one is going to go down by 1. -7, -6, 6 is -5, -4. And then I'm guessing, let's see, -9 over 2. If I paid $9 in 2 payments, that would be $4.50. So I've got -4.5 right there. This one, I would guess, is -5.5. Looks like it's going up by 1/2 as I move down, which makes sense because the slope of this thing is 1 over 2. This would be something I would guess like -8.5, -8, -7.5, right? And I could just go ahead and check that that works. If I get out of this screen, -9 divided by 2, indeed is -4.5. That's what I've claimed here. Once again, I can write each of these input-output pairs in ordered pair format. -2 gets mapped to -9 in this function. -1 gets mapped to -8.5. I'm going to go ahead and fill this out and fast forward so you don't have to suffer through this. Now I've got my input-output pairs. Let's start with the first one. If I go -2 in the x, 1, 2 to the left, I'm going to go -9 down, 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm going to go ahead and skip every other one just because the decimal representation kind of confuses me. If I start at 0 in x, I'm going to go 8 down, 1, 2, 3, 4, 5, 6, 7, 8. This correlates with my knowledge of the slope form because my slope says I'm going to rise 1 and run 2. I go up 1 over 2, up 1 over 2. Lo and behold, when x is 2, y is indeed -7. That's what I see there. Up 1 over 2, up 1 over 2, up 1 over 2. Now I've got this line. I'm going to connect the dots using a straight edge ruler. We check real quick that at x equal 8, which is this vertical line right here, y was -4. I'm going to go ahead and highlight this in red. Here we've defined y2 was -8 plus 1/2 x. Returning to the steps of the graphical technique, we did step 2 in this situation, which was to graph the function on the right-hand side on the same axis. Let's take a look at step 3, which is to find the point or points of intersection between the two graphs. Where does one graph touch the other graph? Looking at the graph, we see right here, this is a really, really special thing. This is called a point of intersection. Some of my previous students used to call this POIs. I'm cool with that. There's the point of intersection. Notice in this situation, because these are lines, we only have one point of intersection. We might expect only one solution. Remember, the graphical technique says solutions to equation happens when one graph touches the other graph right there. I like it when you touch it right there, right there. Returning to the steps in the graphical technique, we have now done step 3, which was to identify the point or points of intersection. In this case, we only have one. Step 4 was to write each point of intersection as an ordered pair in the form x, comma, y. Then we're going to identify the first coordinate, aka the x value of this point of intersection. Returning to this particular value, we see this point of intersection happens when x is equal to 4 and y is -6. We could have also seen that that was a point of intersection from the table because notice that this input value produces the same output in y1 as the output in y2. In other words, for the input x equal 4, the red line has the same value as the blue line. In other words, these 2 points are the same, so this graph, the blue graph, intersects the red graph at that point. There it is. Boom, point of intersection. Recall that we were supposed to identify specifically the first coordinate. There it is. We return to the description of our graphical technique. We have now done step 4, which is to write each point of intersection as an ordered pair. The last step in our graphical technique is to set the variable from our equation equal to the first coordinate of each point of intersection. Moreover, we want to produce a final solution in the form variable equal value. Here we are. We've identified that the point of intersection between this graph has coordinates 4, -6. The first coordinate is 4. This implies that our solution is x equal to 4. Normally, I would say that we must check this work by putting this value back into the original equation, except this is the 3rd time that we've solved this problem, and indeed, x equal 4 is the value that we verified in our previous examples. Thus, the check is the fact that we've verified that this technique produces the same solution. We have now finished the last step of our graphical technique, and notice that the graphical technique produced the same solution as our algebraic technique. I'm really proud of y'all. We just finished our first introduction to the graphical technique. 5 steps. First step is to take the left-hand side, graph it. Take the right-hand side, graph it on the same axis. Find all points of intersection between the 2 graphs that we did in steps 1 and 2. Write each point of intersection as an ordered pair. The first coordinate of the ordered pair is our solution, and we write it variable equal value in that form, and then we can check. These 5 steps will be the same regardless of equation type. That's one of the really nice benefits of the graphical technique. We don't have to remember the type of equation. We can apply these every single time in the same way. In the next video, we'll get some more practice seeing the graphical technique on a different type of equation. See you there.